Yes,
Yes,
sir.
sir. It's clearly visible.
Thank you. Yes, thank you. So in this session, we're going to discuss the basics of the reinforcement learning, one of the very basic reinforcement learning algorithm, which is the Q learning. All right. So in this session, we're going to see what is reinforcement learning and one of the basic reinforcement learning technique and different notions in the reinforcement learning also, key elements basically in the reinforcement learning we're going to look at. Okay. So we already know what is learning, what is machine learning, what is different types of machine learning. So I'm not going to touch that part. We see the concept of the reinforcement learning. Then we'll also see the Q learning, and we'll also look at OpenAI Zim environment to implement the reinforcement learning algorithms. And we'll also look at one of the applications of the reinforcement learning, that is self-driving cabs. So we'll also implement the self-driving cabs using this OpenAI Zim. So that is the agenda for today. All right. So let us begin the session. All right. So we'll start with what is reinforcement learning. We have already seen. Just review it one more time. So
Excuse me, sir.
Yes, yes.
Sir, the recording is going on, no? Sorry to interrupt.
Yes, yes, yes. It's going on.
Okay, thank you, thank you.
Yeah. So in the reinforcement learning, the algorithm, we also call it as a agent, software agent, or the algorithm, reinforcement learning algorithm, interact with some environment. Environment could be a gaming environment, or it could be a restaurant environment, or it could be a driving environment, or it could be some store, right? Or it could be a home where the robotic mop is cleaning something. All right. So environment can be anything, and the agent takes an action based on the current state of the environment. You see that agent is taking an action. As a result, he is receiving the reward, and also the state of the environment is also changing. And the goal of the agent is to maximize this reward and minimize the punishment. So I had given one example also, if you had remembered. So this is the way that you train your dogs or the way that you train your children or the students, right? So when they have done something really good or whatever is desirable, you may appreciate them by giving some rewards. When they have done something undesirable, you may punish them. For a period of time, they will learn to do only desirable things or only good things. All right. So, like for example, let's say that you are trying to train your dog. You got a new dog, you want to train it. Whenever you throw a ball, you want the dog to get the ball back to you. So what do? You emulate a situation by throwing a ball. So the dog may be reacting in multiple different ways because it don't know how to react in the given situation. So he may be barking, he may be standing, he may be jumping, he may be dancing. All right. So he may be reacting in multiple random ways. So whenever it picks up the right action of picking that ball and getting that ball back to you, you give or offer some snacks to it so that when next time you throw a ball, it will get that snack immediately. Okay, because it want to maximize the reward and minimize the punishment, right? So that is how exactly the reinforcement learning works. The agent is designed in such a way that it maximizes the reward and minimizes the punishment. So at any given situation, it picks up a right action that maximizes the reward and minimizes the punishment. All right. So these are the steps in the reinforcement learning: observation of the environment, deciding how to act using the strategy, and act accordingly. So for that, agent receives a reward or a penalty. So learning from the experiences and refining the strategy so that it maximizes the reward. So this process is iterated until an optimal strategy is found. All right. So that is what the reinforcement learning procedure is. Observe the environment, take an action, decide how to act in the environment using some strategy, and act accordingly. Receive a reward or a penalty, and learn from the experience how to refine a strategy so that reward is maximized. All right. So this process is iterated until the optimal strategy is found. All right. So how is that different from the supervised learning? In the supervised learning, we have a input variables as well as the output variable. The goal is to map this input variable to output variables. So there we are learning some function f of x so that f of x is equivalent to y. Whereas in case of reinforcement learning, the goal is to maximize the reward. Okay. So this is a kind of interactive problem, right? So in a sense that there is no predefined data for this, unlike in case of the supervised learning, right? So the agent creating the data based on the interactions with the environment, right? So agent must be able to learn from its own experience to maximize the reward. All right. And how is this different from the reinforcement learning? So in the reinforcement learning, we are trying to maximize the reward signal instead of trying to find out hidden structures, unlike in case of the unsupervised learning. Okay. So although uncovering the structure and agent's experience can be certainly useful in the reinforcement learning, but that itself does not address the problem of the reinforcement learning, that is maximizing the reward signal, right? So in the unsupervised learning, we are trying to find out the hidden structures, whereas in case of reinforcement learning, we are trying to maximize the reward signal. So we therefore consider the reinforcement learning as a separate paradigm alongside the supervised and the unsupervised learning paradigms. All right. So how this reinforcement learning is different. So here we don't have the immediate reward. I mean, in the sense that we don't know the exact outcome, right? So like, for example, when you take a step in some step in the chess game, do you know immediately whether you're going to lose or win? You don't know that, right? Right. So it takes some time to know that, right? Unlike in case of supervised learning. Whereas in case of supervised learning, when you make some prediction, you know that immediately whether it is the right or wrong with respect to the training data. But that's not the case in case of the reinforcement learning. And here, agent chooses the training data. There is no predefined training data, and based on the actions that the agent is taking, based on that training data will vary. And here we have exploration versus the exploitation, and it's a lifelong learning in a sense that either the agent explores the new knowledge or it exploits the already existing knowledge. It is his knowledge about the environment. This we're gonna see and in the later slides also. All right. The next one is, here we have got a different terminology. Of course, it can be confusing sometimes, but it is easy one. All right. So fine. So to understand this, let us take an example and try to explore the concept through the example. Okay. So here is an example of finding a chest or a treasure. So which is there at 2,0 location. So it's a 3 by 3 grid environment, and agent can start from anywhere, random location, and the goal of the agent is to reach to this chest location or the treasure location. All right. So what are the possible actions? Action space is the agent can move either the direction of east, west, north, or south. So he can move any direction in 4 directions. These are the 4 possible actions. And he can either choose to explore this place or he can exploit the space. And the parameter epsilon caters this decision. So what do we mean by exploration and what do we mean by exploitation? So let's say that you have joined some new company at some new place. I don't know the location of the company. So you have gone to that city and you landed upon one hotel, and let's say the hotel is somewhere here and your office is somewhere here. So because firstly for you don't know anything about this environment, you don't know how to go also, right? So imagine a situation, there is no maps, nothing, you're just exploring it naively. So what do? You may be taking some random steps of moving left, right, or straight, whatever, right? So you may be moving some steps, and let's say that you have taken this path to go to this office. Okay. So when the next day you are going to the office, you have 2 options. One option is explore a new path that is optimal than this path, or exploit already the knowledge that you have or the path that you know and proceed through the same path. Okay, so that is what is exploration versus the exploitation. So exploring is exploring the new possibilities or the optimal way of reaching to this goal, whereas the exploitation is use the existing knowledge to reach to the goal state. So this parameter epsilon caters this decision. Suppose if epsilon is 0.1, then we say that with a 10% probability I choose exploration and 90% probability I choose exploitation. If epsilon is 0.2, then I would say that with 20% probability I choose exploration and 80% probability I would choose exploitation. So to cater this decision, we have one parameter, and that is epsilon. All right. So are you with me so far, following?
Yes, sir.
Everybody following it?
Yes, sir.
Yes. All right. So please let me know if you couldn't follow something so that I can repeat it. All right. So don't hesitate to interrupt me. Then, so whenever, let's say that you are playing a chess game. Okay. So are you interested in maximizing the immediate reward? Or are you interested in maximizing the overall reward?
Sir,
Like overall reward, right?
Overall.
Not just the immediate reward, right? Maybe the step that you are taking at certain point of time may not be fetching the so much immediate reward, but that step is helping you to win the game. Then you would prefer to take that step, isn't it? So we are interested in maximizing the cumulative reward, not just the immediate reward. All right. So fine. So these are the elements of the reinforcement learning. Before we discuss the algorithm, pure learning algorithm, let us try to understand what are these notions or elements of the reinforcement learning. So the reinforcement learning system have the four main elements: policy, reward signal, a value function, and optional model of the environment. So policy defines the mapping of the perceived state of environment to the actions to be taken in those states. It means it is perceiving the state of the environment. It is understanding the state of the environment, and then it is trying to map this state or the perceived state of the environment to the action to be taken in those states. Okay. And the reinforcement learning agent uses a policy to select the actions given in the current environment state. So it is basically given the current state of the environment, it is helpful to map this state to a action. All right. So this is what is the policy. And reward signal that defines the goal. So on each time step, when the agent takes an action, he receives some reward signal. Either it can be a positive number or it can be a negative number. And the goal of the agent is to maximize the overall reward. So the reward signal is used to alter the policy. So it means we have to learn a policy that maximizes the overall reward. So we have to learn the policy. It's not that the policy is defined and we have to just follow that policy. All right. So value function indicates what is, reward signal indicates what is good in the short run, while the value function indicates what is good in the long run. It means reward signal is giving you the immediate reward, whereas the value function is giving you the cumulative reward. So it means if you are at a particular state and if you take a particular action, so it also estimates what are the possible actions if you take this action from the next state onwards, and then it estimates the cumulative reward being in the current state itself. Okay, so it means it computes the value using the states that are likely to follow in the future, and then estimates the cumulative reward. Of course, you can time discount the future rewards. It means you may not be giving a full attention or a full weightage to the future rewards, but they can be given, they can be time discounted. It means, let's say that immediate reward is some 100, and next reward expected is, let's say, some 150. So you need not count it as a 150. You can time discount it. You can multiply it with some time discount factor, let's say 0.5 times 150. And let's say that the next reward is some 200. You need not take the full 200. It can be time discounted by taking 0.5 square times 200. So like this, future rewards are time discounted. It means that you are assigning some smaller weightage than the expected reward, right? So rather than taking the actual estimated reward, you are taking the part of it only, because we don't know what is the future. So that is why future rewards are time discounted. All right. So there is a time discount parameter which we denote it as a gamma. Gamma is the time discount factor. All right. So I hope you are with me so far. Did you understand what
Yes,
is
sir.
policy, what is reward signal, and what is the value function? These three things are clear, right?
Yes, sir.
Yes.
Yes, sir.
The next one is either model-free approaches versus the model-based approaches. So right, this is optional. I said, right, there is one more element, which is the optional model of the environment. It means agent may be having some idea about the environment, or may not be having any idea about the environment. So in a sense that, can we estimate or can we predict what is the next state that is likely to follow based on the probability concepts or the probability distribution given to us about the environment, or we don't have any idea about what is the next state that is likely to follow if I take a certain action? That is decided based on whether it is a model-free approach or it is a model-based approach. So in the model-free approach, it learns exclusively from the trial and error. So there is no modeling of the environment. So whereas in the model-based approaches, we use the planning, which means deciding on a course of action by considering possible future situation before they are experienced itself. So before even you experience what are the possible future situations, you are estimating based on because you have some probability distribution given about the environment. Based on that, you will be estimating the dynamics of the future states based on the current states. Okay, it means you can think of like you are modeling the probability of the next state S dash given the current state and the action. So it means you are computing the likelihood estimation of the future states, and based on that you are taking the action. You are deciding the action to be taken being in the current state itself. So in this presentation, we'll be focusing on the model-free approach, not the model-based approach. Okay, so let us set up the reinforcement learning algorithm. So here we have a Markov decision process, which is a kind of estimating the likelihood of the future events based on the sequence of events that it has observed, or the sequence of inputs that it has perceived. All right. And at each time step, it moves it to the new state with a probability of the action A, and this is moving from state S to state S dash. Okay, so we're not going to use this. This is the setup for the generalized reinforcement learning. It means either model-based or model-free approaches generally. Because we're going to look at only the model-free approaches, I will simplify the scenario and will tell you. So don't worry about if you don't understand a particular notation. All right. So every outcome depends on the state and the action pair. So nothing is depending on the previous state or the actions. So we have a policy. So policy is defined with a pi of S. S is the current state. So this is the mapping of the state to the action. So this returns the action to take in the state S. All right. And the goal is to maximize the overall reward. Okay. So starting from the current state, so it is trying to maximize the overall reward, not just the immediate reward. And please see that. So starting with this time step 0, so initially gamma would be, say, let's say gamma is some 0.5. So what is the initial value for the gamma to the power t? 0.5 to the power 0, right? For t equal to 0. And this is immediate reward, right? Immediate reward. Am I right? Hello, following?
Yes, sir.
So then if you go to the next reward, this is 0. Time step would be 1. T is equal to 0 first, then t equal to 1, then t equal to 2, and so on. So 0.5 to the power 1, and the next reward, s of t plus 1 to t plus 2. Okay, and next one is 0.5 to the power 2, reward of moving from state t plus 2 to state t plus 3. Alright, so you see that future rewards are time discounted. They multiplied with 0.5 here, they multiplied with 0.25 here, and even the future rewards are time discounted more. Alright, and the goal is to maximize the overall reward. Okay, so here gamma can be any value between 0 to 1. So trade-off is immediate versus the future reward. So it means if you take the gamma value to be close to 1, then you are giving more importance for the future rewards also. Whereas if you take the gamma to be some closer to 0.1, you are not considering that, you are not giving that much importance for the future rewards. All right. So that's the kind of parameter to be chosen, right? So here is the value function that computes the overall reward. So this is the immediate reward plus gamma times the future value function being in the next state. All right. So this is a recursive function. Please see that. Please make a note of that. This is the recursive function. So immediate reward. This is the immediate reward plus gamma times. It is calling again the value function being at the next state s dash. Right. So this is recursively defining this. And this is the probability of moving from state S to S dash. So we don't consider this probability if it is a model-free approach. If it is a model-based approach, we have the idea about this probability of moving from state S to state S dash. That's the difference. All right. So fine. So let us see. So this is the probability of moving to next state, and this is the reward of making that move, immediate reward, and this is the value of being in that state. All right. So now you might, according to my estimation, so most of you might have understood it only 40 to 50%. Okay. So let us go through one example so that you will understand it to the maximum extent. All right. So this is a simple example of the agent in the environment. And you know that I've already explained this. This is a 3x3 grid in which one of the grid we have a chest or the treasure. The goal of the agent is to reach to that treasure or the chest. All right. So and the agent is starting at some random location in the grid, and he'll be moving in the different directions to reach to this state. So these are the map locations 0, 0, 0, 1, so on 2, 2. It's not 3, 3. It is a 2, 2 because the indexing is starting from 0, 0. All right. So the agent may be taking the actions like moving east or moving west, north, south, right? And the goal of the agent is to reach to this chest location wherever it is present. So for each of this, environment states, we have the different action spaces. Like for example, if I'm here, what are the possible actions? What are the possible actions if the agent is at this location? What are the possible actions? The agent can move to east or he can move to south. No other direction is possible. Am I right? So if the agent is at 0, 0 location, this is the action space, east and south. Hello, can you tell me what are the possible actions if the agent at 0, 2 location? 0, 2 location?
1, 2.
Or west and
No, I'm just
North
asking the
and
actions,
One
not the
comma.
next step.
north and east.
North and east. This is north, this is the east. Two possible actions. What are the possible actions if the agent is at 2, 2? He can either move to
North and west.
North and west.
north or west, right? So this is the action space defined for each and every possible state in the environment. And if the agent at 2, 0, now no action need to be performed because this is already the goal state, right? So 2, 0 is the goal state where the chest is present. All right. So now the reward we are defining here, the reward is that, so if you reach to this goal state, the reward is 100. Otherwise, anywhere, any movement, any other action, the reward is 0. See that. Suppose if you are at this location and taking an action of east, then you reach to this test. So in this case, you receive a reward of 100. Suppose if you are at 2, 1 and moving to 2, 0, it means you're taking an action of north. Then also you receive 100. So anywhere else or any other movement from any other state to any other state, you receive a reward of 0, right? So the agent receives a reward of 0. So this is the reward signal that we have defined for this particular environment. And the goal of the agent is to learn a policy that maximizes the overall reward. All right. So let us take some policy. Okay. And the policy is trying to map the perceived sequence of the states to the action. All right. So here, let us define some policy. This is not the optimal policy. Just to understand the concept, let us define the policy. And the policy is like this. The policy says, if the agent is at 0, 0 location, take an action of south. Okay. So, and it is also defining that if the agent at 0, 1 or 0, 2 locations, take the action of east. And if the agent is at 1, 0 location, take the action of east. 1, 1 and 1, 2 take the action of north. And if he is at 2, 0, no action. If he is at 2, 1, take the action of west. If he is at 2, 2, take the action of north. So this is what is the current policy. All right. So let us try to estimate this reward or cumulative reward based on this policy. So as I have mentioned to you, don't worry about the policy now, and in a sense that don't worry that it's not an optimal policy. So let us just follow this policy and try to compute the value function being in a particular state. Okay. So we are evaluating the policies. So policy is this, as I have mentioned to you previously. So it is time discounted with gamma, and let's take gamma equivalent to 0.1, 0.5. So, and these are the reward signals. So suppose if the agent is at 1, 0, so what is the value function according to this policy? If he is at 1, 0, what action that it is taking? It is taking an action of east. So if he is taking an action of east, it is moving to 2, 0. So what is the reward that it is getting here? 1, 0 to 2, 0.
100.
100, right? So gamma to the power 0 times 100 and no future states because this is the terminal state. So the reward that or the value function that this action is getting is gamma times gamma to the power 0 times 100. So anything to the power 0 is 1 times 100. This is 100. So this is what the value function that he is receiving. So let us say the agent is at 1, 1 in this location. So according to this policy, what action it should take if he is at 1, 1?
North.
North. Is he receiving any reward for this? If he takes an action of north?
No, no.
No, right? 0 reward. So gamma to the power 0 times 0 plus. So after taking the action of north, to which state he is moving? He is moving to 1, 0.
1, 0.
So if he is at 1, 0, what action he should take? He should take an action of east. Am I right? Is he receiving any reward for this?
100.
100. So gamma to the power 1 times the 100. So what is gamma value? Gamma value is 0.5. So 0.5 times 100, and this is 0. 0 plus 0.5 times 100. and this is 50. So it is the value function at this location according to this policy. All right. So similarly, can you tell me, suppose if the agent is at 01 location, he is at 01 location, then according to this policy, what action should he take?
East.
To east.
East. Is he receiving any reward for this?
No.
No, 0. So if he takes the action of east, what is the state of the environment? He'll be in 1, 1 location.
1.
If he is at 1, 1 location, what action he has to take according to this policy? North.
North.
Is he receiving any reward for this?
No.
Yes, sir.
No reward, 0. And if he takes the action of north, he will be at 1, 0. And what is the action he is supposed to take?
East.
East. And is he receiving any reward for that?
Yes, sir.
Yes.
100, right? So gamma squared times the 100. So this is 0 plus 0 plus 0.25 times 100, which is 25.
25.
So this is the value that he is getting at this state according to this policy. So Kamil, can you compute for this function as well? Sorry, this state as well. 0, 0. 0, 0. Can you tell me gamma to the power 0 times what? What action he has to take? He has to take an action of
The south.
south. So for south, is he receiving any reward, immediate reward? No.
No,
Right.
sir.
Then he takes this action. For this also, he is not receiving any reward. Gamma to the power 1 times 0. Next, he
No.
takes this action. No reward. Gamma squared times 0. And next, this reward, this is 100 gamma cube times 100. Gamma cube is 0.125. So therefore, he will get 12.5 here. All right. So have you understood how to compute the value function according to the given policy at any state?
Yes, sir.
Yes, sir.
All right. So now one more relation, I want you to make note of this. So suppose if I'm at this state, okay. So at this state, 1, 1. So what is the value function that we have defined here?
50.
50, right? So 50, which is gamma to the power 0 times 0 plus gamma to the power 1 times 100. Okay. So can I write it this way? Immediate reward plus immediate reward. This is not gamma, this is immediate reward R. Okay. So don't confuse, because the way I'm writing gamma is looking like R. Okay, but don't confuse. The immediate reward R, this is R. That's why I'm changing it now. This is R reward. Immediate reward plus gamma times value function at the next state. Okay, so what is the immediate reward here? 0. Am I right?
Zero.
Immediate reward is 0, right? And what is the gamma value? 0.5. And what is the value function at this point? 100. Am I right? Thus we have already computed here. Value function of 1, 0. Hello, am I right? So times
Yes,
100.
sir.
Am I getting this? 50? All right. So you can check it for another one also. So let's say that you have at 01 location. What is the immediate reward? Immediate reward is 0.
0.
And gamma is 0.5 times what is the value function at 1, 1?
50.
50. So 0.5 times 50. So which is 25. Okay. So you can check for this 0, 0. So what is the immediate reward? 0, 0, 0. Right. And what is the value function at the next state? That is 25. So this is 12.5. So this you can define a recursive function and then solve for this instead of recomputing things again and again. All right. Yes. I mean, this same thing we are explaining here. So please see that. Let me erase. So this is the value function at 1, 1. Immediate reward gamma to the power 0 times immediate reward, gamma 1 to the power the next reward. All right, send 0 0, and this is move to 0 1, the reward corresponding to that, move to 0 1 comma 1, reward corresponding to that, move to 1 0, reward corresponding to that, and it is move to 2 comma 0, reward corresponding to that. That is 12.5. All right, so all of you agree to me that we can have a better policy than whatever the policy defined in this slide. So like for example here, instead of moving here, if I could move here, that's a better policy. I can reach to the chest with a smaller number of steps. Am I right? Similarly here, instead of moving to west direction, if I move to north direction, then it is a better policy. Hello, agree to me, all of you?
Okay. Optimal
Yes, sir.
solutions.
Yeah, optimal. So how to learn this optimal policy is the question. That's what we are trying to see using one of the algorithm, Q learning algorithm. So one of the very basic algorithm that you start your journey in reinforcement learning with the Q learning algorithm. All right. So that gives you the idea. So we learn a policy pi of s that optimizes this value function for all the states. And we have no prior knowledge about the state transition probabilities because it's a model free approach. And there is no prior knowledge of the reward function as well. So the approach is very simple. We initialize here we have a Q table, by the way. So in the Q learning, we maintain one table, which we call it as the Q table. And the size of the Q table is number of states times the number of actions. Number of states times the number of actions. So how many states are there in this particular example? How many states are there?
9 states.
9 states, right? 0 0, 0 1, and so on, 2 comma 2. And how many actions are possible here at max?
4
East,
actions.
4. East, west, north, south. Okay, so 4 actions. So what is the size of the Q table here? Size of the Q table is 9 by 4.
9 cross 4.
Yes. So initially, we initialize all the entries to 0. Basically, this maintains the value function and just try to continuously update the value function. So we initially take the random action and receive a reward from the environment. And we update the corresponding entry of the state action pair in the Q table entry by computing the value function there. And we randomly restart it if it is in the if it reaches to the terminal state. So please see here that when you are computing the reward, you are taking the immediate reward plus gamma times whatever is the maximum possible reward or the value function that you are getting being in that next state. So that entry we are getting it from the Q table. So it means you are picking an action that maximizes the Q table entry. All right. So here, so this is one thing that is what we're gonna see actually. But in most of these learning algorithms, rather than directly updating, we try to move from the previous entry or previous knowledge to the current knowledge with some step size, learning rate we call it as. So this is the value function that you are computing now, but already you know something about this state action pair. That is the previous Q table entry. This is the old value and this is the new value that you are computing. This is the old value, old Q table entry for a particular state action pair, and this is the new value that you are computing. So instead of completely replacing it, we will be moving from old value to new value with a certain step size, and we call that as a alpha. That means we are multiplying old value with 1 minus alpha and multiplying the new value with alpha, taking the combination of them. So without completely replacing it with the new value. All right. So this we follow, but in our example, we'll be following alpha equivalent to 1. So it means we are just considering this. We are ignoring the previous value in the example. But when you are implementing this, this is the hyperparameter to tune. All right. So fine. So let us proceed. When we see the example, then you will understand it better. So don't worry if you have not followed this equation completely. That's okay. Only thing that you need to understand is that we are updating this Q table entry of the state action pairs based on the random actions that we have taken and the value functions that we have computed for that state action pair. Is that much clear to you all?
Yes, sir.
Yes. So let us start here with this example. So round 1. All right. So initialize the Q table entry to 0. You see that everywhere the reward or the value functions or the Q table entries are initialized to 0. 0, 0, 0, everywhere 0. You please notice that. So now initially start, randomly start then, agent is initialized to some random state, right? So random initial state, let's say it is 1, 1, and let the agent take some random action because he is just exploring the space. He has no knowledge about the environment. He's taking some random action, and let's say the action is east. Is he receiving any reward for this? What is the immediate reward moving from here to here? What is the immediate reward? Immediate
Zero.
reward that he gets is
0.
0. Okay. And what is the value function being in that state? Because the Q table entry, you refer to the Q table entry every time. 0, 0, 0, 1, so on, 2, 2. And possible actions are east, west, north, south. Initially, all of them are zeros. So you refer to 2, 1 here. So 2, 1, and if you take some action, whatever is the action, what is the value here? What is the maximum possible value, whatever the direction that he chooses?
Zero.
It is 0 only, right? Because you have
Initial value is
initialized them to 0. Yes. All right. So it means the total value that you are getting for taking an action east being in the state 1, 1 is 0 only. All right. According to the current Q table, I'm just talking about the current Q table. According to the current Q table, the value function that you are getting for this state action pair is 0. So you update that with 0. Again, anyhow, it is a 0 only. So you update it with 0, 1, 1 and east state action pair to 0. All right. So fine. Because this is immediate reward 0 plus 0.5 times the maximum value from this Q table entry is 0, right? So this is 0. So the resultant is 0. All right. So next one. Again, random action from 2, 1. You are currently at the state and the random action taken is north, let's say. All right. So what is the immediate reward if he takes this action? 100.
100.
Right? And is there any next possible state? That's the terminal state. There is no next possible state. So the value that he is getting is 100. So the update the entry of 2, 0 and north to 100. So 2, 0, 2, 1 and north. This one, 2, 1 and north, update it to 100. All right. So it is updated to 100 here. You see that. Okay. So this one is updated to 100. Please notice that. Okay. That is 100 now. So now because you have reached to the terminal state, this we call it as a one episode. Starting from some random state and reaching to the terminal state, we call it as a one episode, one round. Now because you have reached to the terminal state, no more moves are possible. Again start again with some another random state. So round 2. So start at another random state. Let the random state is 2, 2. So this is 2, 2. And let the agent take some random action, right? Let's say it is north. Let's say it is north. So 2, 2 north. Is he receiving any immediate reward? 2, 2
No, sir.
north.
Zero.
0. And gamma times, if he is at 2, 1, 2, 1, and what is the maximum value that you can get from the Q table entries according to the updated Q table?
100.
100, right? So gamma times 100. So gamma is 0.5, therefore it is 50. So update it to 50. All right. So S dash is 2, 1, immediate reward is 0. So immediate reward 0 plus gamma times maximum value from the Q table entry at that particular state is 100. So multiply it with 100. So this is 50. So because this is 50, update this to 50. What we have to update it to 50? 2, 2 north. 2, 2 and north. entry must be updated to 50. You see that is updated to 50 here, right? So please zoom if you cannot notice that small numbers that you can see in the figure, right? Because that is important to answer the questions. All right. So now you have you are at this state 2,1, and again the agent take a random action because he is just exploring the space now. All right. So let the random action is not, and he receives a reward or a value of 100. Anyhow, that entry is already 100, so you need not update. Even if you update, that is 100 again. Still the 100. All right. No more moves possible. So start again. So let's say after some acceleration, let's say that a random initial state is 0, 0. So when it is at 0, 0, and let the sequence of actions, that random actions that he is taking is this indicated with a green colored line in the figure. All right. So when he is traveling, taking the random actions and moving in this path, okay. So we make some updations. All right. So we'll see what are these updations. So let the agent is starting with 0, 0. All right. So if he starts at 0, 0, okay, I'll just move to the previous slide. So far we only know that this is 100, this is 50. These are only the updated values. All right. So agent, do you remember the path? I forgot actually. This path, right? If I remember, this is the path. Okay. So now if the agent takes an action of east here, this is the east direction only, right? Is he receiving any immediate reward?
No. 0.
No. What is the maximum value being in that 1, 0 state? Everywhere it is 0 only. 0 only. So gamma times 0. There is no updation. 0 only. It's still the 0. Okay. This is still the 0. This is still the 0. Okay. So now if he is at 1, 0, he taking this action. What is the immediate reward? Immediate reward is 0.
0 plus.
And what is the maximum value he get here being in this state? Anywhere, all the
0.
places it is 0
0
only, right?
plus.
0, 0, 0. All 4 directions it is 0 only. So gamma times 0. So there is no updation here also. Then what next action he is taking? Is taking an action of this. What is this direction? East. Okay. So is he receiving any immediate reward?
No.
Immediate reward is 0. Gamma times. What is the maximum
100.
value being in this? 100. So gamma times 100, which is 50. So update this to 50. This entry to 50. It means 1, 1, and what is the direction? East. So this state action pair, we update it to 50. All right. So that is updated to 50. So now he is at 2, 1, and he is taking an action of 2, 2, right? Because he's just exploring the space. He's not exploiting the knowledge, right? So now if he takes an action of this south, what is the immediate reward that he receives?
0.
0. 0. And being in this state, what is the maximum value?
100.
Here.
Here.
50
50.
only, right? 0 and 50. 50 is the maximum. So 0.5 times 50, which is 25. It means this entry we have to update it to 25. So this entry we have to update it to 25. Got it, right? Should I repeat this? Got it, or should I update?
Yes, I got it.
Got it. All right. So now he is at this state and he is taking an action of the west. What is the immediate reward? Immediate reward is 0. And what is the value being in the state? All the places it is 0. So gamma times 0, this is 0. No update. Now again, now he is moving to this. Okay, this state, which is east direction. So what is the immediate reward? Immediate reward is 0 plus gamma times what is the maximum value? 50. 50, right? 50. So this is 0.5 times 50. So this is 25. So it means this entry we have to update. Sorry, this entry we have to update it to 25. Right? Fine. So like this we make updations. So random state is 0, 0. So when you make this movement, we are updating 1, 1 east to 50. This we have already computed and we got it also. and 1 comma 2 east to 25. This also we have updated, right? So like this we make the entries. All right, update the entries. So this is another random initial state, 0 comma 2 starting state, and this is the path that the agent is following by taking the random actions. In this process, we have updated this entry as well as 1 comma 0 and east. What is that 1 comma 0 and east? This entry. These two entries we have updated. So after few number of rounds, all the entries in the Q table will be updated. So after many runs, Q dash is converged. You see that this is the Q dash is converged. Now you pick an action that maximizes the value function at any given state. So please tell me. So the policy is like this now. The policy is you take an action that maximizes the value function at any state. So if you are at 0, 0, what is the direction that maximizing the value function? East or south?
East.
East, right? 50 is the maximum, and that is in the direction of the east. So this is the policy for this 0, 0. If you are at 0, 1, then
100.
0, 1, 0, 1.
0.
What is the maximum value?
25.
25 is the maximum value. It can be
East.
either in this direction or in this direction.
East.
You can take any. All right, you can choose randomly. Right, and if you are at 0, 2, then what is the maximum value? Maximum value is 12.5. That is again in either in this direction or in this direction. You can take any direction randomly. Suppose if you are at 2, 2, then what is the maximum value and which direction?
50.
50, and that is in the direction of north. If you are at 2, 1, then
100.
100, that is the north. If you are at 1, 0,
100.
east, right? If you are at 1, 1, then it can be either this direction or this direction, right?
Yes.
Similarly here. Now, isn't it the optimal policy? This is the
Yes.
optimal one, right? Right, at any state, right? The optimal action you are taking. All right. So the policy is this: pick up an action that maximizes the Q table entry. All right. So according to that, this is the updated policy. You see that this is optimal at any given state. This is the updated policy. All right. So I hope you have got it. How to learn the policy using the Q learning. Clear?
Yes, sir.
Fine.
So that 0, 2.
0, 2. Yes.
So both directions 12.
Both the directions are there. You can choose any of either this or this. Both are optimal one. Clear, ma'am?
Yes, sir.
Yeah. Very simple. Okay, and interesting as well. So now we're gonna see the implementation of the self-driving cabs using this Q learning. All right, and you're using the OpenAI Zim environment in the Python. All right, so let me explain you a bit about the environment. All right, so there are the self-driving cabs is basically picking up the customer at the right location and dropping off the customer at the right location. So this is a 5x5 grid we are working in. Here, if there is a wall, means it's an obstacle, which is indicated with a solid line in the figure, as you see there. It means the cab cannot move in this left direction, or this is what west direction. All right. So now the cab is indicated with a yellow color solid what do you call space. All right.
Car.
Car. This is a, yeah, here it is a car, but in the environment we indicate it with a solid rectangle kind of. In the actual implementation, I'll show you that. And please notice here that there are 4 locations indicated with 4 letters: R, Z, Y, and B. These are the 4 locations. Least like you can think of them like the stops or bus stops or whatever, car stops. All right. So this is the customer location indicated with a magenta color, and this is the drop-off location indicated with the blue color. So in the slides it is like this, but actually in the environment I noticed that pickup location is indicated with a blue color, okay, and customer location, pickup location is indicated with a blue color. It means the customer location. Customer location is indicated with a blue color, and drop-off location is indicated with a pink color. So that is the reverse in the environment that we're gonna see. So please don't confuse that. All right. So now, yes, this is the environment. All right. So
Sir,
uh,
what is that RG? Why
these
is
are the
it?
locations, madam. Locations, stops, possible locations. 4 locations are there.
Okay, sir.
Yeah. All right. So how many possible actions for a car to take? Action space.
3.
No, not at this. In general, at any state, maximum possible actions.
4.
Cab can move in the east,
4.
west,
4.
north, south. In addition to that, it can pick up the customer or drop off the customer. So the action space is 6 actions: east, west, north, south, pick up and drop off. 6 actions. All right. 6 possible actions for the agent to take: east, west, north, south, pick up and drop off. All right. And what defines the state of the environment? How many to know that what are the possible states or number of possible states? First, let us try to understand what defines the state of the environment. Cab location. Hello, cab location is one of the things that determines the environment state. Okay. Anything else? Cab location.
Pick up and drop locations.
Pick up.
Yeah. Pick up. We say customer location instead of pickup location. Customer location. Any other thing? Drop off location.
Drop location.
How many possibilities for the cab location in a 5x5 grid?
1.
25 possible locations. The cab can be at any of these 25 locations, right? In a 5x5 grid. Am I right, madam?
Yes,
The
sir.
possible locations for the cab is 25. And what are the possible locations for the customer? Customer location. What are the possibilities? He can be at any of these 4 locations. Plus, he can be inside the cab as well. So, what are the possible locations for the customer?
5.
5.
5.
How many possibilities for the drop-off location?
4.
4. So, how many total possible combinations? 25 times 5 times 4 possible combinations, and this is equivalent to 500. So there are total 500 possible states. So now can you tell me what would be the size of the Q table?
Sir, 500 into 4.
500 into 6, right? 6 actions. 500 states, 6 actions. What are the 6 actions? What are the 6?
4 direction plus
4
pick up and
direction
drop.
plus pick up and drop off. So the size of the Q table is 500 by 6. All right. Is it clear, sir? Why is it 500 by 6?
Yes, sir.
Yeah. So with this little understanding about the environment, let us also look at the OpenAI Gym environment in which we are going to implement this. So this is the action space, 6 possible actions: south, north, east, west, pick up, drop off. This is the reward defined in this environment, -1 for each step if the step is not reaching to the destination. This is because the negative reward for each step, we want this cab to drop off the customer with a minimum number of steps. All right, as early as possible. -10 for pickup or drop off at the wrong location. We are giving a high negative penalty because rather than taking a longer time, dropping off or picking up a customer at the wrong location is considered to be a highly undesirable behavior. That is why we don't want this kind of behavior, highly undesirable. That is why we are giving a high negative reward for that. 20 for the right pickup and the drop off actions. All right. So high positive reward because this is highly desirable behavior. So this is the reward signal, and this is the OpenAI Zim environment. So this Python library gives us a huge number of test environments to work on our reinforcement learning agents algorithm. So you can see the different environments here, zim.openai environment .envs. What else? Okay. Let me copy this. Not found. I was actually trying a few days back also. I was not getting that. Let us see. Oh yeah. Yes, I was trying to show to somebody. Anyhow, earlier it used to be here. Different environments like robotic arms, different games. There are many algorithms, many environments I have seen, but I don't know, that page has been removed. Like you see that I mentioned some of them is Atari, Box 2D, like that. There are robotics, algorithmic. They have different environments. Maybe they have changed that link. Okay, we have to explore that. All right. So if you have to install the Zim environment, no, you have to install it. If you are using a local Jupyter notebook, you have to install it in this Anaconda prompt, pip space install space Zim. If you are using Google Colab, you need not install anything. You can directly use it. So with this brief introduction to the OpenAI Zim and the problem that we are going to solve, self-driving cabs, let us go on implementing this. Go through the demonstration of the self-driving cabs. Okay. So after installing this Zim environment, you have to import it, import Zim. So, and you have to also create an environment by calling the make function. So here I am calling the make function and the taxi environment version 3. So taxi version 3.env I am calling make of taxi version 3.env. This will return an environment, taxi environment. You can render and see that what is the kind of environment it is. So you see that this is the environment that we get. So which is randomly initializing the state. You see that it is similar to the one that we have seen in the, of course, that graphics and all are not there, but it is similar to that, right? Whatever that we have seen in the slide. There are 4 locations and there are some obstacles. There are some movements. That yellow color solid box is indicating the location of the cab. All right. And that blue color is the pickup location. Magenta color is the drop off location. This is the reverse of that, as in case, not in the case of slide, I mean reverse of the slide. All right. So is it clear? This environment is clear, right?
Yes, sir.
So you can reset the environment and render it again to see that, I mean, every time when you reset and render it again, it will be initialized to another random state. So I am executing this multiple times. Please notice that the state of the environment is changing every time when I execute this. See that cab location is changing, pickup location, drop off location, all the things are changing. All right. So every time it initializes to some new environment. All right. So now action space dot n gives you the number of actions. Okay. So env dot action space dot n returns the number of actions. You see that when I'm printing that, I get 6. There are 6 possible actions. Similarly, observation space dot n returns the number of states. Observation space is the state space. So the number of states are 500. So how did we get this 500? Do you remember?
Yes, sir.
5
Cab locations 5 times 5, 5. Customer locations 5, and drop off locations 4. So 25 times 5 times 4, which is 500. So this is the number of states. All right. And So any given state can be encoded to a number. So see that there are 500 states. All the states can be enumerated to 0 to 499. So at any given state, that can be encoded to a numerical number. So like for example, you see that this is one state. This is indicating that the cab location. The first two numbers indicating a cab location. It means the cab is at 3,1 location in a 5x5 grid. And this is the pickup location and this is the drop off location. Or this is the customer location and this is the drop off location. All right. So this is the 2 and this is 0. So let us now see these states. This is encoded as a 328 state. And let us try to plot the state or show the state. So I'm just setting this number to nv.s is state, which is 328, and rendering the environment now. So now when I render, you see that this is the cab location, which is the 3,1 location. Indexing starts from 0. So 3,1 means this one, 0, 1, 2, 3, 3, and this is 0, 1, 3,1. And 2 is the pickup location, which is indicated with this blue color. All right, this is the second location. And 0 is the drop off location. Drop off location is 0, which is this, indicated with a magenta color. So have you got it now? This is the environment 328. This is encoded to a some number, mapping the state to a some numerical number, which is in between 0 to 499, as there are 500 states. All right, so clear so far? Are you with me?
Yes, sir.
Yeah. And this is the P entries. So P entries are like being in that state, what are the possible actions and what are the next states and the rewards that you are receiving. So the current state is 328 and these are the possible actions enumerated to 0 to 5, and these are the next state. These are the probability values, only 1, 0, 1.0, ignore that for now. And these are the next states and these are the rewards that you are receiving. And the last one is whether it is a terminal state or not, whether it is done or not. All right, see that last three actions. So please remember that you are currently at this state. What are the possible actions? If you are at this state, either you can move in the east direction, or you can move in the north, or you can move in the south. You can't move in the west direction. Suppose if you attempt to move in the west direction, you will be remained in the same state. Am I right? It will be at the same place, right? Fine. So you see that last three corresponding to west, three actions: west, pick up, and drop off. So if you are at 328 location and trying to take an action of west, it will be in the same state, and he receives a reward of -1 because one step is wasted, and that's not the terminal state. That's why false here. And even if you take a direct pickup as the action, so it's a wrong pickup, there is no customer there, so for that he is receiving a reward of -10, and this is terminal state. So it means the state of the environment is not changing here as well. Even if you drop off also, the state of the environment is not changing because the customer is not there in the cab, right? And this is -10 and this is not the terminal state. And these are the actions corresponding to north, south, and east, right? So if you take a direction of north 428, 220, next state is 428, -1 reward is receiving, that's not the terminal state, and so forth. All right. So is it clear what is this P means?
Yes, sir.
Yes. So now we'll try to solve this reinforcement learning solve this self-driving cabs problem without using any reinforcement learning. It means by taking some random actions, we'll solve the problem. So now I'm initializing the starting state to this 328. It means whatever the initial state that we have seen previously, and counting the number of steps that it took, number of penalties, and the number of rewards as well. And frames, initialize it to list to replay the frames. It means, so to replay the actions or the sequence of steps that the agent is taking, I'm adding each and every frame to this list so that I can replay and see a video. All right. So now I'm initializing done to false. It means the agent is not done. It means it is not yet reached to the terminal state. So while it reaches to the terminal state, while it's not done, take an action. How are you picking the action? You are picking a random action from the action space. So to pick a random action, call a sample function. So it picks up a random action from the action space. So now execute that action. In order to take that action, you call the env.step. So when you execute this action, it will receive the state of the environment will change. It will return the next state, reward that it is receiving, whether it is done or not. It means whether it is a terminal state or not, and some other information that we don't require for now. All right. So now I'm counting the penalties if the reward is equivalent to -10. All right. And I'm also appending this frame, rendering of the frame in the ANSI mode to this frames. All right. And I'm also appending other information also, the state of the environment, action and rewards, and counting the number of steps. All right. So I'm finally printing the number of steps and the number of penalties that it took. So now you see that the number of steps that it is taking is 1715 and number of penalties is 582. If I execute it one more time, this will change because of the random steps that the agent is taking. All right. Actually, this is less. So let us go ahead with this because sometimes I have observed 7,000, 8,000 steps also. So that takes a longer time for us to see that video. All right. The sequence of the steps the agent is taking. And you see that. So in a 3x3 grid, the agent is starting at some random location to pick up a customer at the right location and drop off the customer at the right location. He took a 1715 steps, and in between he received a 582 number of penalties. It means 582 number of times he picked up or dropped off the customer at the wrong location. All right. So understood, right? Interpretation of these steps and the penalties. Hello.
Yes, sir.
Yes. So now we are printing these frames so that we can see the movement of the user. So I'm taking this frames list, that whatever that I have filled up in the previous step. Okay. So every time I'm clearing the output to get a feeling of the video display. See, video is what? Sequence of frames, isn't it? Sequence of the images as a frames, right? So each and every possible environment image, we are just playing it off, right? So here, first clearing the output, then printing that frame, then also printing the time step. It means the number of steps, state of the environment, action, and the receive. I'm sleeping for 0.1 second because if you don't sleep, no, you will not be able to realize the step that it is taking. It will be so faster that you can't realize it. That's why sleeping for some time and finally calling these print frames by passing these frames, whatever that we got in the previous steps, these frames as the input. All right. So now I'm just executing this code. You see that this is what has happened, right? You see this is the sequence of these are the sequence of steps that it took, and the step is indicated in brackets in the bottom of that video, and these are the time steps, state of the environment, action that it is taking, and the reward that it is receiving. Understood, right? What we have done so far? Yes. So this is around 1700 plus steps, right? So currently at a 340 step, right? So it will take some time. So as you have understood, shall we move on? Let it take some time and complete this. Meanwhile, we'll try to understand the reinforcement learning implementation. Is that okay? Are you with me so far?
Yes, sir.
Going to the same location repeatedly in some cases.
Same location?
That is, it is moving left and again coming back to the right and but again.
Because it's taking some random steps, no? See, we have solved it without using any reinforcement learning.
Okay.
So random steps it is taking. So it can move east, then next immediately take west. So it will come back because it's a random step.
Okay.
Completely acting randomly. Yeah. Clear, ma'am? Shall we move on? Are you with me so far, everybody?
Yes, sir.
Yes, sir.
Yes, sir.
Thank you. So now we'll solve it using the reinforcement learning, Q learning basically. So the Q table we have to initialize to all zeros, right? And what is the size of the Q table? Number of states times number of actions, right? So I'm defining a Q table np dot zeros, env dot observation space dot n. It means this returns the number of states and times number of actions, env dot action space dot n. So this is initialized to zeros. So now initializing the hyperparameters alpha, which is the learning rate 0.1. Can you tell me what is gamma? Gamma is the time discount factor 0.6. And what is epsilon? Epsilon is deciding what? Exploration versus the exploitation. So epsilon 0.1 means what? 10% probability of choosing exploration, 90% probability of choosing exploitation, right? So here we are initializing the different number of steps or the epochs, penalties, all this. All right. And this is the number of episodes for which we are training this Q learning algorithm. One episode is starting at random state, pick up the customer at the right location and drop off the customer at the right location. It means starting state to the terminal state, we call it as a one episode. All right, like this, we are repeating it for 10,000 episodes. You can train it for 1 lakh because I don't have much time in the demonstration. I've reduced it to 10,000. So the more number of episodes you train, no, more better policy you will get, right? As you are updating the Q table. So every time we are starting with a new environment, a new random state. So by resetting the environment, and then all these are initialized to 0, epochs, penalties, rewards, everything, etc. And done is false. So it means it's not a terminal state. While not done, here we are generating some random number by following the uniform distribution between 0 and 1. And if that is less than epsilon, it means I said no, that with a 10% probability, we choose the random action. It means exploration. So if you generate a random number with a uniform distribution and that is less than 0.1, what is that? It means 10% probability of getting random number between 0 to 1 less than 0.1. Am I right? What is the probability of getting a value less than 0.1? If you generate a random number in between 0 and 1 by following uniform distribution, what is the probability of getting that? Should I repeat the question?
1 by 10.
1 by 10, right? Yes. So the question I will repeat because so many of you have not understood this. Epsilon value is 0.1. All right. So now suppose if I generate some random number by following uniform distribution, some random number between 0 to 1. What is the probability of this random number less than 0.1? Uniform distribution means what? Equal probability of each and every possible value between 0 to 1. So what is the probability of getting value less than 0.1? 10% only, right? Hello? Am I right? Everyone?
Yes,
Yeah.
Yes, sir.
It means with 10% probability, you are picking a random step. It means you are exploring the environment. And with the remaining 90% else, you are picking an action that maximizing the Q table entry, right? Picking an action that maximizes the Q table entry, right? Whatever action is maximizing that state action pair Q table entry, you pick up that action with a 90% probability, which means you are exploiting the knowledge from the Q table entries. So now the action is chosen here, either through exploration or exploitation. Now execute that action by calling env.step. So you will receive what is the next state, reward, whether it is done or not, some other information. So now take the world value from the Q table for that corresponding state action pair. So from the Q table, you are picking the world value and you're also computing the new value. You're also computing the next max. It means whatever the action that maximizes the Q table entry corresponding value you are picking, that is the next max. So np dot max of q table of the next state. It means from all those 4 entries, whatever is maximum that you are picking, that is the next max. So now the new value is computed 1 minus alpha times the old value plus alpha times immediate reward plus gamma times next max. Immediate reward you are getting after taking the action. This is the immediate reward, gamma times the next max. So if you remember, this is what we have seen in the slide as well. Okay, so don't confuse that something that I am discussing newly. So this is the state action you are updating, like 1 minus alpha times q state of action, which means the old value, plus alpha times immediate reward plus gamma times max of whatever is next max, right? That's what we had written here. 1 minus alpha old value, 1 minus alpha times the old value plus alpha times immediate reward plus gamma times next max. Next max is chosen the maximum value here, right? Maximum value here. Got it, right? Any confusion?
No, sir.
Yeah. So we computed the new value and updated the state action pair with the new value. All right. So that's all. Repeat the process. In between, you can count the penalties, count the epochs. All right. All that can be done. You set the state to the next state. All right. And you're printing this, episode number, right? And then finally, you're printing the training is finished. Now you see that. So the episode, initially, you see that initially it took more time to move, but later on, because the Q table entries are updated, it completed very fastly. All right. So now this is the Q table entry that I am printing here. So you see that this is the Q table entry for this particular state 328. You pick up action that maximizes the Q table entry. All right. So now to check the performance of the algorithm, I just took 10 episodes here. You can take more number of episodes, and counting the total number of epochs and the total number of penalties as well. Frames also, if you want to see that how it works, how the movement is happening, number of epochs, number of penalties, all that. So every time in the testing, you're picking an action that maximizes the Q table entry. All right. So counting the penalties and the steps as well, total penalties, total epochs, and finally you are taking the average time steps, average penalties. So you see that very quicker, right? So you see that, please compare it with the random approach. So in the random approach, to complete one episode, it made how many penalties it made? It made 582 something, if I remember correctly. How many penalties? Where is this? Yeah, 582 penalties, right? And 1715 steps. These many penalties it took. Sorry, these many steps it took for one episode, and these many penalties in one episode. Now you're repeating the process for 10 episodes, and average you took. See how many penalties it took? 0 penalties, right? 0 penalties, and average time step is 13.1 only. And I've just trained it for 10,000 episodes. If you train it for 1 lakh episode, no, this average time steps also will be reduced. All right. So it will be so quicker. So you can see that using the print frames also, you cannot even realize that also, right? So it is that quicker, right? Got it. Because the first episode, it is within within a step of 1, it is reaching. All right. So is it clear, everybody? Understood?
Yes, sir.
All right. So one of the interesting problem, okay, at least for those who are learning, they feel very excited. I don't know what about you, but yeah, usually I see when I conducting the offline classes, I see people, there is a spark in the people eyes. I see whenever they see this movement in the cab locations. All right. So thank you very much. Happy learning. So I take this opportunity to thank everybody who supported for this course, short-term course, and I also thank all of you for taking interest in joining this course.